All right. Let me go back to that. Okay. So, good morning, everyone. Thank you for this nice opportunity. I am Francesca Sammarruca from the University of Idaho, speaking on nuclear forces in the medium, getting insight from the equation of state. And before I begin, I like to gratefully acknowledge support from the US Department of Energy. Okay. Okay, stay here for a moment. The goal of microscopic nuclear physics is and has always been to be able to predict nuclear structure and reactions as well from fundamental interactions. So, I mean, at this point, the question is, can a state-of-the-art theories provide all answers? I mean, are we ever getting there? And well, I don't know. As far as I think that to a certain degree, we may. Okay, so after some discussion of this kind, I will present my recent work with neutron matter and neutron-rich systems, which hopefully will be of interest to this audience, at least the MSU one, because you are the host of FRIB. And time permitting, I'm not sure if there will be, but in case, I like work in progress that are going nuclear, the nuclear theory group at the University of Idaho. All right. Okay. Well, let me say that the problem of nuclear physics has engaged the best minds, the best intellects for a number of decades. It seems that nowadays, it seems that perhaps the best way to think of the complexity of the problem is to think of it in terms of a hierarchy of scales, where a scale determines the appropriate degrees of freedom. And so, I mean, we all know the truly fundamental force is the color force between quarks, but there is my cursor, there comes the nucleon with its substructure. And I think the question for nuclear physics is how to best describe the process in C, namely an interaction between nucleons, or maybe there could be another 2, 3, 4, or many in a nucleus, such as this one. And I think the question amounts to asking at which point in, well, from energy-wise, this internal structure here becomes relevant, and for the processes typical of nuclear physics, low energy scattering and well, negative energies in bound state, that internal structure is not relevant. Okay, so therefore we can ignore it. And the idea is that the connection with low energy QCD is not through the degrees of freedom, but which are, some of which are kind of frozen, but through the symmetries of the QCD Lagrangian. Okay. I would like to just to put things in a kind of more compact historical context or perspective. Obviously, I will not go through the entire history of the nuclear forces, which starts in 1930, and also it's not the point here, but just incomplete list of a few milestones, which I think may help understanding where we are at now and why. So, I mean, in the 60 and 70, the one boson exchange model was developed and started to become quite popular. There were also more sophisticated meson exchange models being developed, which went beyond the one boson exchange. Again, like I said, there is large overlap between these very approximate phases. In the 80s, meson theory was really popular, was gaining considerable traction. Of course, the goal of deriving the nuclear force from QCD was not accomplished, and that also led to the development of quark models, which on the other hand were just that. They were just models, okay? I like to think of the 80s and 90s as the high precision era for the nuclear potentials. It became important for people to, well, to get the chi-squared as close as possible to 1, maybe increasing the level of phenomenology. You know, if these forces were applied in the many-body system, of course, they were generally supplemented by phenomenological 3NF. In this way, the two-body part, you know, of your ingredients for the many-body problem can be considered well under control. Okay. But then a problem, of course, phenomenological 3NF is which one do you put in, how do you pick and choose, and so. So, okay, now let me just take a break here. So, moving on, excuse me, small technical, okay, moving on. I think that today there is a general consensus that chiral effective field theory is the direction to go, while the degrees of freedom are nucleon and pion. The connection with QCD is through the symmetries of the low energy QCD Lagrangian and their breaking. The most important being chiral symmetry or conservation of handedness. Here, I mean, great reviews have been written for any level, from any very elementary to very advanced, that I recommend to graduate students who are interested in this topic. So again, this is something I already said. Actually, the predictions can be improved systematically, and most important, at every order. I'll say more about that in a moment. At every order of the chiral perturbation expansion, only a finite number of contributions need to be taken into account. And so together with an organizational scheme to rank order the various diagram, which has become known as power counting, you know, nuclear and few body forces can be developed. They kind of, what can I say, show up naturally, or not so naturally, but I mean, at least they show up where they should show up. So this is a very well-known diagram, very partial, okay, where you see, well, this is the order and this is the power of the order, from leading order to next to leading, next to next to leading, next to next to next to leading, and so on. power counting amounts to making the following consideration, okay, at this particular order of power, kind of diagrams, and diagrams really means vertices, what one can go ahead and determine what kind of vertices are with their strength, with their number of derivatives, what kind of orders vertices are, are allowed, and so on and so forth. The problem is that, as you can see, going higher in order, the number of diagrams increases, cascading actually proliferates. And that's part of the problem I alluded at the beginning. So convergence, good and relatively fast convergence is kind of what would save the day if we can get there. Okay. All right. Now, in my title, originally in my title, I said gaining insight from nuclear matter, and I just want to give an example of what I mean by that, an example of how you gain insight from this idealized system, which is nuclear matter. Gaining insight in what? In the microscopic ingredients of your model, which is why it is so important to work microscopically, in my opinion. So an example, is about exploring the relation between symmetric nuclear matter and nuclear forces. Okay, and let me first show a very introductory slide. Now, the concept of a nucleus as a liquid drop that we think of since 1950 is, of course, a very simple one, but certainly not fundamentally wrong. It's almost been at the foundation of nuclear physics since many decades, and particularly if you think of bulk properties. If you take your best density, mass formula or liquid drop inspired functional, okay, and then which of course is supposed to describe well, a large part of the nuclear chart, and then you throw away terms which have got to do with the surface, limit size, and Coulomb. What you get, and even the asymmetry, unless you want to keep it, what you get is an infinite idealized system, symmetric nuclear matter, which saturates at about 0.16 inverse Fermi cube with an energy per particle of about minus 16 MeV, plus or minus 1. For reasons, symmetric nuclear matter has been traditionally a test bench for nuclear many-body theories, and simpler for the theorist, given the infinite nature and the related translational invariance. Okay, so so that's kind of the relation between nuclei, phenomenological description of nuclei, and the so-called empirical experimental values for saturation, which of course are not really measurements done in nuclear matter. So what do microscopic approaches predict for such relationship, meaning the relationship mentioned up here? Okay. Okay, why don't we move on? Okay, let me frame the issue here. Let's see. So the issue is as follows. We are talking about chiral 2 nucleon and 3 nucleon forces. and in their combination. And the arguments I will advance are equally valid at N2LO or N3LO. So for simplicity, I will make this exercise at N2LO. Now, here is the issue, okay? The issue here. So there are combinations of 2N, 3N chiral forces, which predict the binding energies and radii, point or charge radii, for a wide range of nuclei, but they are unable to saturate nuclear matter. Well, this is kind of a, yes, the key point here, the key man, key person, Hute 2019. On the other hand, if the saturation constraint is included, oh, I should have said, I mean, along with Triton binding energy constraint, because everyone wants to have that constraint and describe the binding energy of three-nucleon system realistically. So beside that, we include the saturation constraint, then medium mass nuclei are systematically underbound, and consequently radii are too large. Here I refer you to work by Hoppe and collaborators, recent from 2019. Okay, so what I want to do next is to kind of explore this apparent inconsistency and see and discuss what I have learned from this exercise. Okay. All right, let me go down. Okay, as far as our ingredients, now I show things I calculated. So our ingredients are for the 2-nucleon force, the 2NF, for that we use high quality, accurate nucleon potential, which exists as a family from leading order to fifth order by Enten, McLeod, and Nozick, 2019. The 3NF, all right, let's show all of that first. The 3NF, these are the diagrams of the leading chiral 3NF, which appears at N2LO. 2 pi, 1 pi contact and contacts. These are the standard definition. Standard convention refers to these as the X, or low energy constant. CI from 1 to 4, CD and CE. These constants are prefixed. They are fixed in the pi nucleon system, and actually nowadays they have been fixed with very high precision through a Roy-Steiner analysis. Well, this constant here must be determined to get, I mean, within the 3-nucleon system. Okay, subleading, there are very many, and I just calculated those, and here I just show you for your information. Again, these are typical diagrams, okay, not at all of them. They are regrouped by topology and topologies, and each topology contains many diagrams. We have a 2 pion, this is 2 pion, 1 pion, and the ring. This is part of what the general topology is called ring type, and these are shorter range contribution. Okay, so let's see if I forgot something here. So these are the ingredients. Okay. Reference 1, reference 2. Let me put out the most relevant information here. I I know that Christian Drischler is in the audience. I don't know if it's still there, so I'm happy about that. Okay, so these are low energy constant pair of CD, CE, which have been fitted in reference differently in reference 1 and reference 2. Reference 1 fits to trito binding energy and the saturation constraint. There are three possibility, and the CE comes, I mean, three possibilities are given. This is the corresponding CE. These are pairs. So when you fit the binding energy of hydrogen, of triton, you end up with a trajectory, which is a relation between CD and CE. And then you pick on that trajectory, you pick a pair. This is a CD-CE pair that the best suits your need, the best satisfies, describes the observable, which you have chosen. So these are values from Drischler and collaborator, excuse me, Moite and 2LO and 3LO, and this is reference 2. With CDCE of this size at 2 and 2LO and N3LO respectively. So if I had to take something away from this graph, I would say, not knowing anything else, I would say that, wow, there is a large difference in values of these low energy couplings, depending on how you fit them, on how you determine them. So, okay, that being said, on to the equation of state of symmetric nuclear matter, red and green. Okay, let me give you first the information that you need most. Okay, so again, red, there you have it. There is a corresponding code here. Reference 1 gives you this saturating curve. Okay, and reference 2, the green, has a bit of problem, and I cannot stress enough that both sets of legs predict the binding energy of triton accurately, and the green, in addition to triton, gets a constraint from binding energy of oxygen-16, and quite obviously it lowers quite dramatically the EOS at higher density, determining, using just colorful words, kind of a nuclear matter catastrophe. So let me see. Okay. Right, this has it all. So this is what I got, calculating my equation of state using these low energy couplings. Okay. I also made a calculation. That's also my way of doing it, because I wanted to calculate ground state energy and charge radii, but in a way where the equation of state was the direct input, actually. Okay, so I won't get into the weeds of that. I find what I was expecting to. Here I did it: oxygen, calcium 40, calcium 48, and lead 208. And these are the ABC sets of pairs here. Most definitely there is a systematic underbinding. These are the experimental value, and the charge radii are they are larger, consistently with less binding energy, and these are the experimental value. So okay, now Some time ago, the dash dot green, dash dot green, this curve here that refers to this curve, dash dot green, and which I will refer to as and that's for developed, and whereas the dash green, the only dash, my connection is unstable here, only dash is is Habeler force plus 3 nucleon forces. This interaction, it is my understanding, was obtained from SRG evolution of to get a low momentum interaction, a softer interaction, starting from the force that's known as EM 2003 18.2.0 in terms of 2NF and 3NF cutoffs, plus of course the 3NF, and was fitted, and the constant were fitted to Triton binding energy and the proton radius of helium-4. Before I go on, I should say, I don't know much about this. I never really work with SRG, but SRG is a unitary transformation which soften the interaction by removing some correlation from the wave function. Basically, the result should be independent of the basis if the basis is complete. However, in practice, there are truncation also in a nucleon space. Bottom line is that whatever is taken away to make your interaction softer somehow appears elsewhere in the form of induced three-body forces, which are not included in this interaction. Just to have a definition to use for the future slide. Not officially, this interaction, this force was often not often, I heard it dubbed as the magic interaction, the magic force, because it saturates nuclear matter nicely and also provides a good description of closed shell nuclei from all the way from helium-4 to nickel 78. The work here for the nuclei is by Simonis and collaborators 2017. So now, again, because even though this certainly may give us a indication of what the direction to go is, it is not a full solutions because of the inconsistency with the SRG evolved and the non-evolved 3NF case. So some people ask, okay, can we construct a realistic, obviously realistic, but there 2NF, which is not SRG evolved, but is as soft, as the force, as the Habeler force from reference 3. So it is my understanding that the answer so far is no, and probably may remain no. So I am told that vigorous efforts were undertaken to attempt this solution of this problem. The blue and the red and the purple are the softest. I mean, lambda 400 MeV, I certainly wouldn't go any lower than that. Softest unpublished interactions by EMN, Ente, McLeod, and Nozick from third to fifth order. And let me see if there is anything else I wanted to say. No, I think this is it. So this is where we are at for that particular situation. I would like to summarize in case they have gotten lost, I would like to summarize the observation, put them in a nutshell. So clearly the value from CD, and by the way, it is CD, not CE. CE as a, because I detangle the various pieces, CE has a much, much weaker impact. So when you fit oxygen 16 together with triton, then you have the nuclear matter catastrophe. A three-nucleon force which binds the triton and includes the saturation constraints provides, as we have seen, insufficient binding in medium mass nuclei, and I think the US is still slightly on the repulsive side, but not so much. If you relax the triton constraint, this is what I read from the paper. If the triton constraint is relaxed, not abandoned, I presume, but relaxed, then the resulting lex will allow for a better description of medium mass nuclei, and at the same time, the triton will be underbound. And so my conclusions, everybody could conclude that this suggests that the need for a 2NF and 3NF combination that provides sufficient attraction at lower density, but still enables saturation. More bullet points to put things in, to summarize things, what that I already said. It's amazing to see how large the difference are for the CDCE when you fit them through different observables. And as far as I know, a combination of simultaneously optimal CDCE, which would work for the few nucleon system, medium mass nuclei, and nuclear matter, has not yet been found. I propose two scenarios, both of which are being tried with little success. Either super soft two-nucleon force combined with a strongly density-dependent three-nucleon force, or, super soft, like the one that people have tried to produce with 400 MeV cutoff, or a moderately soft, like they are available, two nucleon force combined with a 3NF, which is attractive at low density, but turns repulsive at and above saturation. And judging from what I have seen and other people have tried with CD, if they are negative, if they are positive, what they do at low density, what they do at higher density, this seems to be not easy to come by. Okay. And so that was what I meant with getting insight from the equation of state. If your equation of state is phenomenological, then you really have no idea what's going on in there. Whereas here we are trying to understand components of the 3NF one by one. Okay. So, all right. Variety of things. So let's move to another system, the one I promised, which is neutron-rich matter. And let's go down a little bit. First, some neutron-rich matter 101 equations, which you all know, just to remind ourselves what are the things that we are talking about. So this is the particle in isospin asymmetric, this one, isospin asymmetric nuclear matter in the parabolic approximation, where alpha this is the definition of the symmetry, isospin asymmetry parameter, and this is the definition of the symmetry energy within, obviously, within this approximation. And okay, and this of course is the expansion, where we also make reference to that. That's the expansion of the symmetry energy around saturation density, which defines the well-known parameter L. K is poorly constrained, second derivative, but L is obviously related to the density slope of the symmetry energy at saturation density. Okay, so what do we have? Well, okay, so first of all, I should show my equation of states, my equations of state for pure neutron matter, energy per neutron as a function of density. So this is the last I have. It's the last because I have all the subleading 3 Newton forces, the 500, I mean, going to another cutoff changes hardly anything. Subleading forces in 3LO, so N2LO is fully at N2LO, N3LO is fully at N3LO, and of course, just for comparison, I have the leading order and the next. And what we want to take away this picture is, well, for the low, this lowest anyways, is the small impact, maybe 1 MeV or so, is the small impact that the leading, 3NF at N3LO bring about, maybe an MeV or something in the direction of attraction. Okay, so, okay, let's keep this in mind. This is kind of now will be my main ingredient, okay, in what comes next. I change notation here. Instead of E sim rho 0, that's what everybody calls J. And this is not J, this is the energy per particle, per neutron at rho naught with its error, 16.6 plus or minus 1.2. Maybe not a huge, this is truncation error basically. So this is J, an important quantity. Okay, this is my J. This is my L. I take a moment here so that you can look at it. 55.7 plus or minus 9.1. So this is something around the 50s, 50 to 60 or so. Okay. I also calculated the pressure, the neutron matter pressure at rho naught, which is moderate. I mean, it's in the order of 3, I don't know, a little bit less maybe or so. So this is a very important quantity. It is has a chief role in the radius of the canonical mass neutron star, 1.4 solar masses neutron star. Okay, so this is what I find. I wanted to, there is a myriad of calculations, of course, from all theory and myriad of constraints, but I wanted to gauge myself with a recent calculation analysis based on chiral EOS and good precise calculation of error. This is a Bayesian analysis by Drischler, Fernstall, Melendez, and Phillips, if I'm not incorrect. Apologies if I am. And this is the value they show in that preprint. Well, I would certainly say that I am happy with the level of agreements. And also, I would like to add that I have never seen microscopic theoretical prediction, okay, not analysis with phenomenological model, microscopic prediction of the J. They would be much different than, I don't know, 31 plus or minus 2, or L from the microscopic standpoint, much smaller or much larger than this, let's say 100 on 120. That does not happen with microscopic prediction. So let's move to the neutron skin of lead-208, which I have here in the order of 0.16 or so. And no matter how I calculated correctly or not, I mean, this is to be expected if this correlation is to make any sense, as I'm sure it does, then, and my L is somewhere here between 50 and 60, then I would be very surprised to have a radius, which is up here, or maybe down here. So it seems like, according to phenomenological analysis, the correlation, the famous linear correlation, I am where I should be. Px2 values are, and Px2, I mean, I don't, it must be published by now. So I saw the preprint in January 2021. Px2 value for the J, well, that's high, 33, 34 to well over 40. The L, the density slope of the symmetry energy, has a central value of 106, an upper limit of 140. The pressure, which I calculated with the back of the envelope, formula here, is a lot of pressure. The skin is 0.29 plus or minus 0.07. Again, remember my the correlation before. This is, of course, consistent with such L, I presume. And okay, this is the skin, but let's go on. This is my comment. It's wow. I mean, they are high. I mean, well, they are among the highest I've ever seen. And I am not the only one to say that, because here, this result challenges myriad of experimental measurements and theoretical predictions, as stated by the authors, I mean, some of the participants of the Px2 themselves. But I would slightly rephrase this and say that myriad of experimental measurements and theoretical predictions challenge this result. And the citation is here, myself, today. So, okay, this is the Px. Now, of course, some optimism here. The jury is still out on many things. First of all, the 3NF at N3LO, as many people in the audience know better than me, have a limited degree of flexibility. First of all, it was already predicted some time ago that before they were calculated, that they would not change dramatically. They would not solve any of the big problems because they have, well, they are generally small due to the kind of vertices, okay, and they have a limited degree of flexibility. So on the other hand, even though this is a little bit uncomfortable because it seems to indicate a slower convergence of the chiral effective field theory, slower than expected or desired, some components of the 3NF at N4LO may be necessary. Okay, so I don't know, I haven't done anything in N4LO, and I suspect that the full calculation with all the diagrams at N4LO will be a nightmare. But people like Ghirlanda and collaborators, his name is Ghirlanda, and I should say it correctly, being born in Italy. So Ghirlanda and others, if you look at this paper, it's quite interesting. This is not a complete calculation. This is an exploratory calculation where it seems that some component would solve And then again, we don't know, because when you have everything in, there are cancellations. So some components would solve the well-known AY puzzle, which is the famous problem in polarized proton-deuteron scattering. Okay, so honestly, I think this will not have much to do with bringing the L parameter from 50 to 120, but I mean, there is still, and this is a little bit what I said at the beginning, you know, we don't know where we need to stop, because things in the expansion become cumbersome. But N4LO is a place to look into at this time. And okay, maybe just to give you an idea, so these are one loop diagrams at N4LO. I have done nothing with them, and there are also 3 diagrams appearing at N4LO. Somewhere here that seems to lie the solution for the AY puzzle, and maybe other problem. Okay, and speaking of neutron-rich system, of course, as long as I have time, you know, I have to touch upon, you know, the EOS and neutron stars. I don't have to convince this audience of the chief role of the equation of state in calculating the structure of neutron stars. So it is the usual cartoon with not in scale, definitely not in scale, with the unknown, mostly unknown, I would say unknown core. Okay, so our prediction for the pressure in beta stable matter, stellar matter, because that's what you need for neutron star. They, excuse me, they look like that. Here I have a small footnote disclaimer kind of to make. My most recent equation of state, which I showed a moment ago, I have not yet applied them, recalculated the neutron star with the stellar matter and neutron star. So what this means, but I guess it's the problem is very small. There is no problem. The legend here is as follows: N2LO means 2NF at N2LO, 3NF at N2LO. N3LO means 2NF at N3LO, and the 2NF. And the 3NF is at N2LO plus an important contribution, the 2-pion exchange, which is included through effective low energy couplings. It's easy because it has the same mathematical expression, okay? And the same legend goes for N4LO. The 3NF, the 2NF is at N4LO, the 3NF is at N2LO, except for the 2-pion contribution. So these two guys are a little bit hybrid. Is that do I worry about it? And there is also some cutoff dependence here shown. Well, first of all, you may notice how the order by order variations are very, very small. And I'm not going to go back to that. My time is running out. If you remember my most recent equation of state, particularly the red and the green, where I have included fully the 3NF, the subleading 3NF, the difference was extremely small. So if there is a difference in the neutron star predictions, as I will show them, if any, it will be very small and possibly in the direction of attraction, of softness, okay? Okay, so for this part, those are my ingredient, my input EOS. And Let's see, I'm gauge my time. Okay, so of course, chiral effective field theory is not going to take us to Fermi momenta corresponding to 5 or 10 times saturation density. So we actually So we extend the microscopic EOS with polytropes. I'll say more in a moment. This is not at all a claim that this is an EOS is going to take us all the way to the core. There is no such object at the moment. This is just a way to continue the EOS so we can study what we want to study, which is the sensitivity of the radius of the canonical mass neutron star to high to whatever may happen at high densities. Okay, so and of course you have to attach a crust, which I take from the literature. So we express our chiral prediction stop at twice rho naught. We express the high density pressure with polytropes, which look like this. And by varying the adiabatic index between 1 and, I don't know, 1.5 to 4, that's enormous, okay? And I got guidelines from studies, phenomenological studies, mostly from J.C. Reed. Okay, so then we can have a feeling, we can have, because we do it piecewise, so like this, maybe matching density, and then we attach the polytropes, and then we attach them again. And so you have a piecewise matching, and we have an idea of very soft or very stiff at different density, like could be the case if there is a phase transition or something. So yeah, so that's what we do. And like I said, we wish to explore here the sensitivity of the radius of the average mass neutron star to the corresponding spreading of the prediction, which is this fanning that we show here. And again, anything at super high density can only be phenomenology, and it's certainly not to replace, that doesn't replace a microscopic theory. So, okay, we find after we, we just put everything in the TOV, in our TOV machinery, then we get together with the constraint of maximum mass and causality. Yes, I know the maximum mass it's 2.1 now, but since we are looking at the radius of the 1.4 mass, 1.4 solar mass neutron star, this limit changing a little bit will make no difference. So, and of course the causality constraint. Well, okay, this is the usual M over R relation, and estimates for the radius of our canonical mass neutron star is around 11, is that thing here. P-Rex2 gives these this range. LIGO Virgo, if I'm not mistaken, but I don't think this is the ANALA and others, 2018, they provide an upper limit less than, and this is a little bit critical with respect to this prediction. I believe that soon after this article, this paper was published, Fatoyev and others concluded that from this upper limit, the upper limit for the neutrons, for the skin, this is the skin of lead again, it should be 0.25. Again, the P-Rex result is 0.29 plus or minus 0.07. Okay, then the threshold density for the direct ORCA are consistent with P-Rex2, are very, well, they're very low, but there is no time to get into that. conclusion up to this point. How am I doing time, Mr. Host?
Yeah, you have like yeah, just a few, really just 1 or 2 minutes left.
1 or 2 minutes.
We want to have some questions.
Okay. Okay, well, then I kind of put the conclusion there. After decades of struggle, the 2 nucleon force seems to be under control. Will open question in nuclear structure be resolved by chiral EFT? It is not clear. The approach is conceptually pleasing, at least that's what I think, but the proliferation of many nucleon forces with higher order may be a serious challenge. As for the neutron matter EOS, we will continue to proceed microscopically and systematically as we have always done. Experimental programs such as yours or JLab are very important. It's important to couple with strong theoretical support. And thank you for your patience. Thank you very much.
Thank you for the interesting talk. Are there any questions? Please raise your hand or just unmute yourself and ask. Pavel.
Yes, I have a question. Thanks, Francesca. So I have a question. You said there's a myriad of experimental and theoretical results in contradiction with the Purex2. I'm sorry that the theory of everything doesn't work, but as to empirical experimental results, can you mention one that's in contradiction with Purex2 that I should treat on the face value?
You mean one theoretical prediction?
One experimental result that contradicts Purex2.
Oh, well, I can mention, maybe it's easier this way, maybe like 1,000, not 1,000, but
no, I mean, I'm sitting inside the results, so
yes, and that's
not my view.
No, that is my view. Well, that is the view of the authors of Purex, and these are, I believe, relativistic mean field model, which are and these are, they're not experimental. So experimental when it comes to this kind of things is a matter of definition. What you do, you seek constraint. By experiment, I mean empirical constraint.
I have results on the same quantity that Purex measures, which is 4 years old and is identical to Purex.
Which one is that?
This is analysis of elastic scattering and charge exchange, quasi-elastic charge exchange, which measures isovector size of the nucleus, and the difference of the isovector size compared to isoscalar difference is 1 Fermi, and is absolutely consistent with Purex2.
Oh, that's nice. And a myriad does.
Well, there are a myriad of people who try. I mean, symmetry energy is fashionable, so people try to connect to it, and they do
not me. I calculated.
No. That's all right. No, I'm not questioning your way up from simpler systems to more complicated, but at some point there is an issue: what is the skin and how you measure it? So people try to connect other observables to neutron skins, but the connections are made through theories, through variety of evoking systematics, but they don't address directly, just like Purex, the size.
Yeah, and there is an analysis involved, but you see, as far as I'm concerned, you can take this neutron skin, you can just, throw it away for a moment. People may calculate it or analyze or extract it differently, but I think we all are capable of making a derivative here, and so let's stay with the L parameter being so large, the pressure being so large, the direct ORCA limits being so low. I don't want to connect to anything. I mean, I have done calculation with different theories. Basically, my point is from analysis. I mean, you cannot measure the skin. You cannot. Well, Pirex wanted to measure the skin of lead 208 with weak interactions, so that you don't have uncertainty coming from strong interaction, another way of analysis or so. So that was the weak interaction was what Horowitz brought up 20 years ago that we do, but it's not something that you measure directly. So there could be.
I don't question that there is a tension, the issue of attention, but there are very many wannabe results, okay, where you say, well, I can connect to symmetry energy and I end up with something safe, so it's not controversial, it won't be questioned. And not controversial is the middle, and middle is 50, okay? So you have very many results like that. Anyway, that's just my comment.
But I mean, yes, and that is worrisome, right?
Yeah.
Because it is an inconsistency.
Yes.
If you measure a cross section and I don't fit it, okay, then most likely you are giving me the data. Most likely something is wrong with my theory. I mean, I don't know. When you give me an indirect analysis, I'm not questioning the experiment. I'm just saying it's a problem, and
there's a problem, of course.
Where do we go from here?
Of course, yeah.
I thank you very much, and stay in touch. Send me an email with references.
Sure. Thanks.
Thank you.
Okay. Any more questions?
Yes. Hi, Francesca. It's Betty. Yeah, okay.
Oh, hi, Betty. Hi, nice to see you more or less again.
No, so my question is this, that for the P-Rex experiment with the neutron skin, actually it doesn't matter if it's P-Rex or anything. The neutron skin experiment measure, even the Horowitz and everybody agree that they measure at the density of 2/3 of rho zero, not at rho zero. And so my question is, and even in Horowitz paper, I don't think in Horowitz it's Reed. I think it's the first author. I forgot the first author. I think it's Reed. Even in their paper about the P-Rex too, they show that their L, they really measure L is at 2/3 of the rho zero. So my question is that why don't you guys, the theorists, compare that L? Don't go and extrapolate to the rho zero. Rho zero is attractive because it's rho zero, and also the L give you the immediately symmetry energy. But I think that the theorists should compare L at 2/3 of the nuclear matter density, not at rho zero, and maybe you will get better agreement.
Yeah, well, the definition of L from the expansion is the quantity, but now L to rho zero. So are you saying that this value, this 106 that I have now,
this 106 value become, I think maybe 60 or something like that, is in their paper. If you do it at rho over rho zero, you go 2/3. So what I'm saying, yes, everybody expanding about rho zero, but you can also expand it around rho 2/3 of rho zero, because that's a fixed point. We have masses, we have a lot of things that we know.
I don't have to extrapolate. I mean, I can just interpolate. I can calculate. I spline.
Yeah, you can calculate. That's exactly what I'm saying.
That is not a problem at all. It would take me a second. But if this is, since the symmetry energy grows, is this the value of rho zero? Then a 2/3, then a rho zero will be even larger.
No, no, no. The L in here that was shown by the P-Rex2 value, they already extrapolate from L. They already extrapolated. But in their paper, they also list the L, what I call L.1.
Right.
Yeah, so I'm just saying that not just to you, but to all the theorists. Maybe they should compare the L.1, not the L at row 0.
Well, you know, 2/3, I mean, and 1. Yes, 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 I know what you mean. But yeah, I think I have it in previous paper. You know, as you can imagine, 2/3 and 1, this pressure and L, I mean, my value will not change dramatically, but I am more than happy to calculate them at any density whatsoever. Microscopically, I mean, I don't have to extrapolate anything, but thank you so much for your suggestion.
Okay, any other questions?
Yeah, and I also want, as another comment, that, you know, you talk about, for sure, that I think FRIB will also play an important role in the future for the equation of state. But I think that is very important. And as a matter of fact, our paper just published today, to have data points about saturation density. And you can only get that from heavy ion collisions.
Okay.
Okay, I can refer to you to our paper, you know, that will give you a S0 at, I mean, not S0, the symmetry energy around 1.5 low 0. So and that has a really large level arm, you know, much more than the P-Rex result.
Oh, yes. So it's another system. Okay. Great. It's a recent experiment that you just published?
Yeah, we just published, just came out, I think last night. We just noticed that it's online. So I can send that to you.
Please do.
Send a link to you. Okay.
Please.
Okay, are there any other questions? If
I have a few questions. I'll try to make it quick. So I want to just have a better understanding of what you were doing. So earlier you were showing the equation of state that you were calculating from Christian's and some other guy, I don't remember, another paper.
Yeah.
And I was wondering, so were you using MBPT to do those calculations for infinite matter?
Oh,
to get those equations of state?
Many body perturbation theory? No, I took the constant from Christian, but I calculate my equation of state with a non-perturbative Bruckner-Hartree-Fock.
Oh, I see. Okay. Okay. So yeah, thank you. And another question I had was that you were showing some unpublished data with 3N forces. And you were saying you had this idea of using a softer potential. And they tried doing that. Yeah, and I just thought it was weird because it seemed like when you went to a higher order, the saturation got worse. You know, you went from N3LO to N4LO, and the saturation is worse. And that, I was like, how do you explain that? Like, what's going on there? Or am I seeing that wrong?
Let me think. When I went to N2LO and N3LO.
No. Yeah, like N3LO, the red, compared to N4LO, which is the purple.
Oh, this guy. Oh, sorry, this guy.
Yeah, in the plot. Yeah.
But there is no saturation here. Oh, you mean closeness to saturation?
Well, it got worse, right? It didn't, because it's supposed to be, right? It's supposed to be what, the dashed line, right? Where it's saturating.
Yeah, the dashed line, yes. The dashed line is the Christian, what I call the Christian force plus 3NF. This one is 2NF only, and it's super soft because it has been evolved.
So all of them are there's no three body forces in all of these.
No, not at all.
Oh, okay. Thank you. Because I was confused by that. And the last question is, why do you choose to fit the, I don't remember, is it a CD or one of those constants to the, or CE. Why do you choose to fit that to oxygen 16? Is there any? Is there?
Yeah, I don't see. I do not. In fact, it's done in reference to, and apparently my point was I don't actually. I have in my those hybrid model that I show. I usually take them from the PISA group, Triton, and maybe some, I don't know, Triton beta decay observables. No, these one are really to address the current problem of intermediate mass nuclei. I chose oxygen. My feeling is that because these people here, it's what they have done, and they have gotten very nice predictions for intermediate mass nuclei all the way up to nickel isotopes. I presume that if they took another nucleus in this mass range or similar, would be the same. I do not. I'm just trying this. This choice here is the one that gives you the nuclear matter catastrophe. So I'm just trying values taken from other people and insert them in my equational state.
Okay. And this is the last question, actually the last question. I realize it's actually the most important.
Yeah.
So I think some of the few slides over, you said you took the equation of state and you tried to use it to predict energies for oxygen for different
Yes.
nuclei. I think it was a little bit further ahead. And I was wondering, and I'd heard that, okay, so maybe I misunderstood here, but I've heard, and maybe this is what Pavel was saying, that if you're trying to take the equation of state for an infinite system and you're trying to extend it to a finite system, you can't just take the equation of state because there's like a surface term and there are other complications that you have to deal with. So is that, does any of that come in here, or am I just misunderstanding?
I don't want to get, no, the way I do it, it is not a microscopic calculations of these nuclei, but it may be simple, but it is quite direct. It's not extrapolating. So I have a density functional, okay, because I believe that the idea is not completely wrong, particularly for bulk property. I have a density functional, which is liquid drop inspired. So there is the volume term where you can also add the asymmetry. There is the Coulomb, there is the surface. When I take the thing there and I, starting from some initial parameter, and also for a particular, for say a 2-parameter Fermi, could be a 3-parameter Fermi or so, there is some uncertainty there. And then I minimize the energy of the system with respect to the parameter of the density distribution, okay? So I obtain at the same time the parameter, so the parameter give me the minimum of the energy has to be minimum. With those parameters, then I can calculate nuclei. So it's not an extrapolation, it is a simple, but it's the only way I know to just enter the US directory, which is what I wanted. But there is surface, there is Coulomb, there is everything that should be there in a simple way. And I wanted to just get to see kind of the systematics, and that is there.
Okay, so the way to, if you were trying to do it, I'm just saying this for myself, the way, one of the ways that you could try to do it is with density functionals. Is that, so that's kind of like.
Yeah. I mean, what goes in the equational state is microscopic. The way is an approximate one, is a simple, but I think it's pretty good to be the systematic. Yeah, it's I have tested that method. It gives very, very realistic result unless you have a highly deformed nucleus or some strange things. Okay.
Thank you.
You're very welcome.
Thanks. So we are out of time. If there's nothing really urgent. So Christian, you have just unmuted, but.
Yeah, so if I may, just one more minute, Roland, is that okay?
Okay, yeah.
Sure. So hi, Francesca, I'm Christian, nice to meet you. And thanks for your talk. Just 2 quick comments on or in slide 11. where you showed the low energy constants and compared between reference 1 and 2. So I personally just quickly, I'm not too much concerned about the difference in size between the two references, because they're, I mean, how they were constructed is conceptually so different. I mean, reference 1 is, I mean, our potentials are bare interactions, while 2 are SRG evolved, both NN and 3N interaction at the same order though. But I'm more worried about the fact that, for instance, CD here is 10 or 9, so pretty large. And I was wondering on the next slide where you showed the catastrophe in symmetric nuclear matter, whether all many-body frameworks that are based on a basis expansion are efficient enough for those interactions. So if you, I think Küter increased the cutoff, I mean, studied the cutoff 500 and 550 MeV as well, and CD and correspondingly CE were much smaller in absolute value. So it might be worthwhile investigating the 500 cutoff instead of the 450 MeV.
Yeah, I haven't. You mean for the Roth equation of state?
So sorry, for what equation of state?
For the Hütter calculation?
Yes, or both, right? So we also have 500 MeV, but in particular here with the Hütter, so I mean they have one table in the paper, as I'm sure you know, and if I remember correctly, 500 and 550 are way smaller in absolute value than 10, and I'm just concerned about the many-body convergence in all calculations. With those potentials.
50 very much, because I stay with 50 at most, because I have been told that above that perturbative properties are not very good. But I did try. I think I did look at even calculate things with 500 with these guys here. Didn't change dramatically. And by the way, if you notice also here, well, let's go to 13 again. I have not attempted to calculate the nuclei with the CDCE that are 10 or 9 or whatever, because I mean, they show them, they are good. To me, with a meaningless equation of state, it doesn't make sense. And by the way, with the method that I use, putting in the EOS and looking for minimum, it doesn't work, because the minimum will go, judging from the green curve, will go down and down and down. So anyway, but yeah, thank you for your hint. Thank you very much.
And then one last point, I was just being curious. So in your N4LO calculations with approximated 3-body forces, or even at N3LO with approximated 3-body forces. So could you do, so what about the truncation error and the convergence? So my point is, so could you estimate, I think in one of your papers you have done this using the EKM uncertainty or some variation thereof. So could you estimate the truncation error up to the order, up to which you include all 2- and 3-body forces consistently and completely, I should say, and then see how the higher order contributions that are partially approximated match with those uncertainty bands, if they are, I mean, contained within that uncertainty bands, in particular at higher densities beyond nuclear saturation density. So say up to twice the nuclear saturation density.
Yes, I can do. The error I calculated for the non-hybrid model, I mean, the one, well, let's take just value. You do it for observables. Yeah, I can do it point by point. I calculated this error with the formula. I don't know how to call it. Are you familiar with the Applebaum paper in European Journal of Physics?
Yes.
So I take that formula to, and I think the errors tend to be pessimistic rather than optimistic. So yes, I can do that.
Okay, thank you very much.
Thank you.
Okay, we have really run